In the past few videos, we've mostly looked at molecules with a single chiral center. So we usually have one central carbon, 4 unique groups attached, and this allows for our 2 different enantiomers. Now, of course, in biological molecules, we often have dozens or even hundreds of atoms connected together in very large molecules. Since each of our carbon atoms generally wants 4 bonds, it's natural that we'll tend to have many different carbons that each have 4 unique groups attached. This means that we'll have many chiral centers in our biological molecules. For small molecules like sugars, we'll often have a handful of chiral centers. For large molecules like proteins, you might even have hundreds of chiral centers in one molecule. So, what do we do when we have multiple chiral centers? Do we still have enantiomers? How many enantiomers would we have then for a molecule with multiple chiral centers? So in order to answer that question, we're going to look at a small organic molecule that still has multiple chiral centers. So if we look at our molecule here, we have our carbon on the left. It has our methyl group, a hydrogen, and OH, and our other carbon over here attached. That's 4 unique groups. So we have a chiral center. Now over on the right, we also have 4 unique groups attached. Again, oxygen, hydrogen, our methyl group, and our unique carbon over here. So we have 2 chiral centers. Okay, so the first thing we can do, of course, is look for our enantiomer. So we take our structure, here we have our mirror image over here, and we create our enantiomer, right? So even though we have 2 chiral centers, we can still create our 2 enantiomers from that molecule. So again, notice the perfect mirroring. If I rotate this around, again, because these are enantiomers that are asymmetric, I'm not going to be able to superimpose on each other. There won't be overlap between our 2 molecules. Now, if I take a closer look, using our rules, I can also determine what the configuration is here. So my hydrogens are both pointing to the back. These are my low priority groups because they have our low atomic number. Oxygen has the highest atomic number, so it's going to be my highest priority group. Then next I have my 2 carbons that are tied, but this carbon has an oxygen attached. So that's going to be my second highest priority, and this is my second lowest priority. So this is priority for my carbon over here on the left. My hydrogen is already pointing backwards, so I don't have to rotate my molecule. I move from the highest towards the lower priority, and I'm going in a clockwise direction. So my chiral center on the left is the R configuration. My chiral center on the right will also have its own configuration. So for my chiral center on the right, I again rank the oxygen as the highest priority, the other carbon with the oxygen as the second priority, my carbon up here is the third priority. My hydrogen is already in the back, so I can immediately move from the higher priority to the lower priority. I'm again moving in the clockwise direction for an R configuration. Now over here I have my mirror image. As always, my mirror image is going to have the opposite configuration as my original molecule. In this case, that means it's going to be S and S. I'll go ahead and confirm that just to show you. So this would be number 1 priority, number 2, number 3, and number 4. Lowest priority is already pointing towards the back. I'm moving counterclockwise for that S configuration. Now you'll notice here I have 2 chiral centers, each that can be either R or S. So what if I take that same molecule and I draw it with just switching one of my chiral centers? So I'm going to draw my chiral center on the left exactly the same as up here. So this is still going to be R, it's still drawn exactly the same, still exactly the same relative orientation. My chiral center on the right, I'm going to switch my oxygen and my carbon so I get a structure that looks like this. So again, I can determine my configuration. 4, 1, 2, and 3 is my priority. My hydrogen is still in the back, so I go from my higher priority to my lower priority. I'm moving counterclockwise to give me an S notation for this chiral center. So as we compare our new molecule with our previous molecule, you can immediately notice that they don't look like mirror images, right? My oxygens are both pointing up here. Up here, one is pointing up and one is pointing down. So it's not mirrored, or we'd expect both of my oxygens to be down here as a mirror of my structure. Same thing with my carbons. They're both pointing down and towards me. Up here, I've got one pointing towards me and one pointing up over here. So they're not mirror images of each other. They also have very different shapes, right? If we move this up and try to superimpose it on my other molecule here, my hydrogens would perfectly overlap, but my oxygens and my carbons wouldn't line up. So it's not an identical molecule, but it's also not an enantiomer because it's not a mirror image. So this is a diastereomer, which is a stereoisomer, and that it differs in terms of the spatial positioning of our atoms, but it's not that mirror image that we get with our enantiomers. So this is similar to the diastereomers that we've seen with cycloalkanes, where you can have the trans with one group pointing down from the ring and the other pointing up, or the cis where they're both pointing in the same direction. So you can kind of see a similar arrangement here, where these are kind of pointing in opposite directions versus pointing in the same direction for our oxygens on these two different molecules. So whenever we have multiple chiral centers, we'll have some enantiomers. Enantiomers will always have the opposite configuration at every chiral center. So note that we have the R for both of our chiral centers, and we have the S for both of our chiral centers for the enantiomer. And that will indicate our enantiomer. Our diastereomer has a different configuration at one of our chiral centers, right? We switched from R to S at one chiral center, but our other chiral center still looks the same. So again, different positioning at one location, but not at the other location. So we don't have that complete mirroring, but we still have a different structure. So if our enantiomer occurs whenever we have our configuration switched, we should have another enantiomer to this diastereomer, where we take our RS and switch it to our SR notation. Now here we can use a little quick shortcut. Anytime we're switching our configuration, we can just take our structure and switch any two groups in order to change that configuration. So in order to switch that from R to S, I'm going to replace the oxygen with my carbon and replace the carbon with my oxygen. And I'm going to go over here and I'm going to replace the oxygen with my carbon and the carbon with my oxygen. So I switch my chiral centers, I should have a new enantiomer. Right? Across my dotted mirror plane, all of these should be related as enantiomers. And then between these groups, we would have diastereomers. However, as I look more closely at this molecule, you might notice that if I take this and rotate it around, these actually look very identical. And it looks like they would superimpose on each other if I rotated it. And in fact, if we look very closely, we can see that this molecule is completely symmetrical around the center plane here between our two carbons. Right? It's actually perfectly mirrored from one oxygen to the other, from one carbon to the other, from one hydrogen to the other. Anytime we have a symmetry like this, we can't have enantiomers. So this molecule has symmetry, therefore it can't have an enantiomer, and these are actually identical in this case. So sometimes when you have multiple chiral centers, we can actually still have symmetry, and we can have compounds that are identical even though they look like they have different configurations at those different chiral centers. So we call this a meso compound. So a meso compound is a compound that has multiple chiral centers, but is still achiral. Of course, again, achiral refers to something that is symmetrical. We notice that here with our plane of symmetry between the two carbons. So as we add more chiral centers, we are going to see multiple different arrangements of our molecule. Normally, since each of our chiral centers has two different possible configurations, R or S and R or S, we'll have 2 to the n different possibilities, where we're just, n is the number of chiral centers, and so we're basically taking the number of chiral centers and the number of different possibilities and multiplying that together to get the overall number of possibilities. So here we have 2 chiral centers, 2 raised to the 2 is 4. We have our 4 different possibilities, but in this case 2 are actually identical because of that symmetry here in our molecule. So we normally expect this many different possibilities. Some of those might be identical if we have meso compounds with some amount of symmetry in there that makes some of our enantiomers identical. So we get unique diastereomers when we change one or more, but not all of our chiral centers, and we can get our enantiomers when we flip our configurations to get the opposite configuration at each of our chiral centers. Now again, this is still a relatively small molecule. We only have 2 chiral centers, only 4 carbons overall. For a lot of our biological molecules, we'll see many more chiral centers. We will still see some meso compounds, although as we get to larger molecules, they tend to be relatively asymmetrical.